Hello, greetings. So I assigned you all a fun isentropic compression problem, and I've received a couple of questions on it. And so I want to kind of go through the setup behind it to make sure you're all on the same page and are able to get it. And so basically the problem is that we're looking at a process, okay, in which we go from some initial temperature and pressure, okay. So we have a fluid at a given initial temperature and pressure. Then we're going to isentropically compress it. All right, so delta S is going to be equal to 0 to some final state at some temperature, final temperature T1 and pressure P1. Okay, and what you're given is we're given T naught and P naught, the conditions of our initial state. We're also told the final pressure P1. Okay, and then for the second part of the problem, you're going to be asked to use the SRK equation of state, and so you're provided with TC, PC, and omega. All right, my parameters for my SRK equation of state, and then also we're given a polynomial expression for CP, and so just to write the first couple of terms, we'll say that CP is equal to A plus BT plus CT squared, right, and so on and so forth. Okay. Cool. And then knowing all of this, we are asked to find or compute T1. Okay. So what are you going to do? Okay. So this is what we're given, right? So we are isentropically compressing a fluid from some initial temperature and pressure to some final pressure P1 and asked to solve for what that final temperature is. And so kind of, where I think the students that have reached out to me are getting a little off track is they're going to previous chapters in the text and trying to use expressions that are provided therein. Okay, and so one of the comments they made at the start of the class is that one of the challenges with thermo is that there's so many equations out there, and oftentimes the issue is that the origin of those equations is unknown to the user, which then causes problems in using them and implementing them. Okay, and so that's not something that I'm saying to be critical of you all, but that's true in general. And so one of the goals of this course is to try and get you not to fall into that trap. Okay, and so what I would encourage you to do for this problem is not look in previous chapters of the text, but rather essentially derive the working expression for yourself. Remember back in chapter 5, right, we said that thermo is nothing but two laws and a little calculus. So starting from our combined statement of the first and second law and a little calculus, we can generate the working expressions that we need for ourselves. Okay? And so let's go through exactly how to do that. Okay, and I'm going to start with the case of an ideal gas. Okay, and just as a reference, I'm going to go back to our type notes from chapter 5, in which we have derived a whole range of expressions, and those are also derived in screencasts also posted online. Okay, but I'm going to start with our type chapter 5 notes. Okay, there's a screencast in which we go through all of this, and I'm going to look for the example in which we work out an expression for entropy with independent variables T and P. Okay, so here we work out an expression for entropy with independent variables T and P. Why I'm thinking about entropy with independent variables T and P is think of the problem at hand. Okay, so and also again, just keep in mind if I have a single component, single phase system, I have 2 degrees of freedom that I need to specify. So given that I know the initial temperature and pressure, and I know the final pressure, and I'm asked to solve for the final temperature, temperature and pressure would seem like the natural independent variables that I would want to work with for this problem. All right, so I immediately think about, okay, an expression for entropy with independent variables T and P. Then you can go back through our derivation. Again, we also have a screencast on this. You would get to this final equation, where then if we plug in the equation of state for an ideal gas, we get this final working expression. Okay, so you would get that for an ideal gas. Okay, ds ideal gas. ds ideal gas is equal to Cp ideal gas over T dt minus R over P dP. Right, so just checking, yeah, minus R over P dP. All right, so then what does an isentropic process look like? Right, an isentropic process is going to be one in which delta S or ds equivalently is 0. So what I want to do is, if I'm trying to solve for the final temperature, let's integrate this animal. Okay, so delta S, okay, which is going to be equal to 0, will be equal to integral from T naught to T1 Cp ideal gas over T dt minus integral from P naught to P1 R over P dP. Okay, now Cp ideal gas, the heat capacity of my ideal gas, is only a function of temperature. We're good here. We can tackle this. And here we just have R over P. R is a constant. I can integrate that, no problem. Okay, so let's do it. Okay, let's do it the correct way, and then let's take an aside to get an expression that you may be pulling from the text. Okay, all right, so now this expression here, okay, so we are given, and actually let's take an aside, okay, just to simplify it, take it in steps. Okay, in the problem, you're given a polynomial expression for Cp. And actually, I believe that it's actually presented as Cp ideal gas over R. That way it's dimensionless. But, here for illustrative purposes, all right, let's just take Cp ideal gas to be this simple, second order polynomial. Okay. Can't remember if it's 4 or 5 terms used in the problem I gave you, but here let's just truncate it after 2 for convenience. But polynomial expressions are typically how ideal gas heat capacities are tabulated. Okay, so if I work with that, okay, just to take this in steps to make it easier on myself. Okay, so if Cp ideal gas is A plus Bt plus, and I'm just going to write a Ct squared. Again, you would have additional terms. So that Cp ideal gas over T would be A over T plus B plus Ct. All right, and again, you would have extra terms. Okay, so I'm just going to take this, piece by piece. Okay, so therefore, the integral from T naught to T1 Cp ideal gas over T dt. Okay, I could equivalently write that as integral from T naught to T1. I'm going to break this into pieces, right? I just have addition over here. A over T dt plus integral from T naught to T1 B dt plus integral from T naught to T1 Ct dt. Oop. Get a little close to the edge of the screen. Okay. So then if we integrate it, here's where we test Professor Paluch's calculus skills. Okay, so this first term, so integral from T naught to T1, A over T dt. So antiderivative of this is A was just a constant, so you could pull it out. Antiderivative of 1 over T is log T. Okay, so this would be A times log T1 over T naught. All right, so A log T1 minus T naught becomes log ratio. Okay, plus, okay, B is constant, pull it out. Okay, so this would be B, then just the integral of T, so that becomes B T1 minus T naught. Okay, plus C is constant, pull it out. Okay, and then it's going to be the integral of T dt, so that would be a 1/2 T squared. Okay, so I'll write this C over 2, and then that would be T1 squared minus T naught squared. Okay, cool. Okay, and that's again assuming I haven't forgotten too much from my calculus days. Okay, but antiderivative of T should be 1/2 T squared. Okay, so that's that part. Okay, the second part is just integral from P naught to P of r over p dp. Okay, so r is constant. I could pull it out. Okay, antiderivative of 1 over p again is just log p. Okay, so log p1 minus log p naught. I get r log p1 over p naught. Okay, so putting it all together, okay, for my case of isentropic compression, I have that 0 is equal to a log T1 over T naught plus B T1 minus T naught plus C over 2 T1 squared minus T naught squared, and then it's minus R log P1 over P naught. Okay, so let me box this in. Okay. And again, I'm going to sound like a broken record, but your expression here, the integral of Cp would be longer because you should include those additional terms. Okay, they're all simple powers of t, so it should be pretty straightforward to integrate. Okay, but anyways, when I look at this final expression, okay, I know T naught, right? T naught's known, T naught's known, T naught's known, P1 and P naught are known. R is just a constant. Then A, B, and C are known parameters that were given for a heat capacity model. So here then, the only unknown is T1. So I have a single equation with a single unknown. So I wouldn't recommend trying to explicitly solve this equation for T1. But you can readily solve for it numerically, whether you're using Microsoft Excel and you want to use GoalSeek or Solver, or MATLAB, you can readily solve this with F0. But you have a single equation with a single unknown. Okay, cool. Using that, you should be able to solve for T1. Okay, so that is the case of an ideal gas. Okay, nice. Okay, any questions? Well, I guess you can't really ask questions, but if you have any questions, just by all means let me know. Okay, and so here I'm going to quickly take an aside. Okay, I want to take an aside with an expression that you may have seen for isentropic compression in your Thermo 1 course. Okay, and again, this is thinking back to equations of unknown origin, right? So someone sent me an example problem from chapter 4 in which this equation was provided. But at that point we hadn't derived all of our expressions yet. So let's do it here, and let's kind of talk about what they were doing in that problem. Okay, so if I go back to my case of isentropic compression, okay, for an ideal gas, okay, I have the ds ideal gas is Cp ideal gas over T dt minus R over P dP. Okay, so for the case of isentropic compression, okay, for an isentropic compression, ds ideal gas is 0, so I just have 0, right, is Cp ideal gas over T dt minus R over P dP. All right, so this equation that we have boxed in, all right, I would say that is the rigorously correct way to solve this problem. Okay, and when I said how to solve it, right, again, I didn't recommend trying to solve it explicitly for T1, but instead I would try and solve it numerically, whether it's using Solver in Excel or F0 in MATLAB. Okay, now while we can readily solve these problems numerically on the computer, 50 years ago might not have been such an easy task. Okay, and so oftentimes simplifications are made to make these problems easier to solve. For one, but then also simplified expressions can also make it easier to do back of the envelope types of calculations, and also to just conceptually walk through problems. Okay, so simplified equations do have value, and so you should know where these things come from and how to apply them. It's just for this specific problem, go the rigorous route, since we're trying to calculate a numerical value. You have a computer, you have time, and you're provided with all the information you need. Okay, but anyways, one common simplification would be assume, okay, Cp is constant. Okay, and so if you had a very small temperature change, assuming CP is constant, might not be so bad. But let's just assume CP is constant. Work out an expression, and then talk about how you might estimate CP. Okay, and so why might I want to estimate or assume CP is constant? Well, then I have 0 is equal to, okay, now if I want to integrate this animal and CP is assumed constant, now I have CP, ideal gas, times integral from T naught to T1, 1 over T dt, minus R, integral 1 over P dP. Okay, and this is integral from P naught to P1. Okay, so by assuming CP is constant, then I get that 0 is CP times log T1 over T naught minus R log P1 over P naught. Okay, now we play with log rules. Okay, so a constant times log of T1 over T naught. Okay, this is equivalent to, I could bring this up as a power, log T1 over T naught raised to the CP. I could do the same thing here, minus log P1 over P naught raised to the R. I'm going to bring this over to the right hand side so that I have log P1 over P naught raised to the R is equal to log T1 over T naught raised to the CP. Okay, so now compute the exponential of both sides. Okay, and I have P1 over P naught raised to the R is equal to T1 over T naught raised to CP. Okay, and a way that you've probably seen this presented before would be P1 over P naught is equal to T1 over T naught raised to the CP divided by R. CP over R is nice because it's dimensionless. Okay, cool. All right, and so this would allow you to say solve for an equation that's explicit in P, but you could just as well solve for T if you wanted. So namely, P1 over P naught raised to the R over CP would be T1 over T naught. Therefore, T1 I can explicitly solve for is being T naught times P1 over P naught raised to the R over CP. Okay, so this equation is nice in that it readily allows us to solve explicitly for T1. Okay, so that's nice and easy. I don't need a computer. I can just do this on a simple graphing calculator, simple calculator. But this equation is also good because it gives you a way to quickly estimate what that change in temperature is for a given change in pressure. All right, so for a given change in pressure, so if you want to increase the pressure by a factor of 10, well, the temperature is going to increase by a factor of 10 raised to the CP over R. Right, so if say the factor of compression needed, it allows you to readily estimate what that factor of increase in the temperature is. And so this could be incredibly valuable for back of the envelope calculations, quick estimates. These sorts of calculations are good when you work with a process simulator, who becomes the ultimate black box in churning out calculations, checking the reasonableness of those values. If I can quickly do or perform an estimate like this, and then the process simulator gives me something that's off by a factor of 100, something's going on. Right, so these things are valuable. These are the equations that were presented back in chapter 4. Now, in chapter 4, there's an example similar to the problem in which they solve it using this equation. And so what they do is basically they start with an initial guess of CP as being CP evaluated at T naught from the CP expression. Then using that constant CP, they solve for T1. Then they calculate a log mean temperature and use that to estimate CP. And then they keep iterating until T1 converges on a constant value. Okay, and so it's iterative, but each iteration you can directly do the calculation on your calculator, and then just keep repeating. Okay, even that sounds like it'd be a lot better on a computer, but it's feasible to do by hand. Okay, so here's the equation that you probably saw here in your Thermo 1 days. Okay, that's where it comes from. Okay, only simplification that's being made here is Cp is being assumed constant. So over narrow temperature ranges, that should be a pretty good assumption. But in general, the utility of this equation is for some ease of calculation. Okay. For the problem I gave you for essentially homework, you should just do the full rigorous calculation because you can, right? It's not that difficult to work out this equation, and then it can readily be evaluated numerically on a computer. Okay, so cool. Okay, and since we're on the topic, let's talk just a little more. Okay. All right, so that's the case of an ideal gas. Okay, now let's talk about a real fluid. Okay, and so in this problem we're going to use SRK, the SRK equation of state, suave over the Kwong. But if we were to use any old cubic equation of state, it'd be just the same. And essentially key there would be the parameters we need are Tc, Pc, and omega, which are provided. Okay. So, how would you solve this problem for a real fluid, right? It's essentially the same, right? So delta S, my actual change in entropy, right, which is 0 because it's an isentropic process, now is going to be equal to delta S ideal gas plus delta S residual. Okay, that's all there is to it. And so 0 would be equal to, okay, so I would start with this equation here, which is delta S of an ideal gas. Okay, and so this will take a couple of lines. So this would be a log T1 over T naught plus B T1 minus T naught plus C over 2 T1 squared minus T2 squared, or T1 minus T naught squared. Okay, and that should be minus R log P1 over P naught. Okay, cool. And then I need to add to it delta S residual. Okay, so plus I'd have S1 residual. Okay, now remember, think about your black box, right? So there's SRK code online for working with SRK equation of state. And so basically, you can think of the SRK as a black box. In goes, so in this case for state 1, T1, P1, Tc, Pc, and omega, and out comes residual entropy. All right, so this would be, we'll just say a function of T1 and P1. Okay, you could think of Tc, Pc, and omega being parameters, minus S naught R, which is a function of T naught and P naught. Okay, so it's essentially the same problem. Again, solve this animal numerically. Well, for an ideal gas, you can simplify the equation like such, so that you can solve it explicitly for T. Sorry, you're out of luck here for the case of a real fluid. All right, but it'd be the same thing if I look at the expression. I know A, B, and C. Those are my constants for my heat capacity equation. I know T1. I know P1 and P naught. I know R. Okay, I know Tc, Pc, and omega, which are the parameters for my SRK equation of state. So the only unknown in this equation is T1. All right, and so using, say, MATLAB, you could readily solve for, MATLAB with F0, you could readily solve for T1. But it's something you're going to have to numerically solve for. If you want to do it by hand or in Excel, you could. All right, basically you could say guess the value of T1. Maybe you take your ideal gas value from the first part as an estimate, calculate delta S, And then, based on that, keep, guessing a new temperature until you converge on a value of delta S of 0. Okay. But yeah, here I'd probably, more so advocate in, the for MATLAB. While S naught R could be calculated directly because T naught and P naught are known. S1 residual, the challenges for each guess value of T1, so if you're trying to solve this by hand, you would need to solve SRK equation of state. So first you would solve for your Z's. That once you have your Z's, then you can use that to calculate your residual entropies. And if you have more than one real root, you need to choose the appropriate root, and so on and so forth. And so MATLAB, readily allows you to automate that. Okay, but I think that's it, right? So it's just a matter, from there of doing. The other part of the problem is looking at isothermal case. Isothermal case is a lot more straightforward. If you were to calculate, say, delta S or delta H of an ideal gas, so dH is CP dt. So dt is 0 for the isothermal case. So delta H is 0. In terms of delta S of an ideal gas, again, dt is 0. And so, all right, so if I have an isothermal case, dt is 0. So this term would go away, and you would just have that pressure-dependent term to get you the change in entropy. Okay, and that would give you delta H and delta S for an ideal gas. And then, once you add on the equation of state part, well, then it becomes a little more challenging. But certainly using, computer, it becomes doable. Okay, hopefully that helps.